An ozone molecule forms when an oxygen molecule encounters an oxygen-free radical. So if we draw an oxygen molecule with its double covalent bond, then we consider what happens if an oxygen-free radical happens to be nearby. We could imagine that the oxygen-free radical want to make a single covalent bond, maybe even a double covalent bond with the oxygen molecule. The only problem with that is this oxygen already got its 8 outer shell electrons. This oxygen has 6 outer shell electrons. So there's no format of normal covalent bonding that's going to satisfy both oxygens' need to get 8 outer shell electrons. So something else happens instead. And that something else is called a coordinate covalent bond. What happens instead is 2 of the free electrons from the oxygen-free radical actually pair up. What happens next is these 2 electrons from this oxygen are actually donated to form one covalent bond. So the end result looks something like this. And this here is known as our coordinate covalent bond. In this particular bond, both electrons have been donated by the one atom, whereas in regular covalent bonds, in the bond, one electron comes from each species in the bond. Once it's formed, this coordinate covalent bond is identical to a normal covalent bond, but it's given this special name, coordinate covalent bonding. So that's the structure of ozone, and ozone has a double bond and a single coordinate covalent bond holding it together. And this shape and structure of ozone gives it some distinct properties versus oxygen. Both of them are covalent molecular. So both of them typically have low melting points and low boiling points. We already said that oxygen, O2, was a non-polar substance. But ozone, despite the fact that it's made of only the same type of atom, 3 oxygen atoms, actually has a slight dipole. So it's going to have slightly different properties to oxygen. The reason why it's got a slight dipole is a little bit complex, so I'll explain it now. If we look at the ozone molecule again, we have the central oxygen, which is double bonded to another oxygen atom. That oxygen has 2 pairs of electrons. The central oxygen has a pair of electrons. We have our single coordinate covalent bond, and that's bonded to this third oxygen, which has its 3 pairs of electrons around the outside. Now, there's a few ways of thinking about why oxygen is polar. The simplest way is that this central oxygen has to share electrons with 2 other atoms, whereas these 2 oxygens on the outside only have to share electrons with 1. And that means this central oxygen has a slightly positive charge compared to the other end of the molecule, which has a slightly negative charge. If you want to think about that a bit more, if you think about where the electrons are, it might make things a bit simpler. If we imagine each separate electron in these bonds, so we can see all the electrons around any particular atom, and we realize that in a covalent bond, these electrons are shared. So at any one time, each oxygen, well, they're sharing both, but at any one time there might only be 1 around any particular oxygen. So if we add up all the electrons around each oxygen, we can start to see there's an imbalance of electrons. If we add up the electrons around this first oxygen, we have 1, 2, 3, 4, 5, 6. 6 electrons around that most of the time. Around this oxygen here, we have 1, 2, 3, 4, 5. 5 electrons around that oxygen most of the time. And around this oxygen down here, we have 1, 2, 3, 4, 5, 6, 7. It's clear to see this top oxygen will typically at any point in time have less electrons around it than these 2 oxygens down here, giving this molecule a net dipole, with this central oxygen being slightly positive compared to the rest of the molecule. There is no net dipole side to side, even though we've written 6 and 7 here. It's for a complex reason that this here actually forms something called a resonance bond. In actual fact, this bond here actually flips between both sides of the molecule. So the electrons are actually evenly shared between these 2 oxygens. Even still, we still have a net positive pole up here and a net negative pole down here because of the uneven sharing of electrons in the oxygen molecule. So ozone is actually polar. Now, being polar, ozone has a slightly higher boiling point, melting point, and water solubility than oxygen. There is one other factor to consider though. It's not only because it's polar that it's got a high boiling point and melting point. The polarity does contribute to that. Another reason why it's got a higher boiling point and melting point is just because it's heavier. It's got 3 atoms compared to 2, and therefore it takes more energy to vibrate. But at the end of the day, the polarity is the only way to explain why it's got higher water solubility than oxygen. It's got a few other features compared to oxygen. Ozone is actually a slightly pale blue, whereas oxygen itself is clear. So that's a summary of ozone. We've looked at oxygen free radicals, we've looked at oxygen molecules, looked at the structure of ozone, we've looked at coordinate covalent bonding, we've then had a detailed look at the structure of ozone and why it's slightly polar compared to normal oxygen.